All right, welcome everybody to our online lecture for today. Um, so the way this is going to work is it's going to be similar to how we do lectures in class. However, when we do a problem, it's going to be up to you to pause it and try it. And I really want you to do that to see if you can get it before I show you the answer. If something is confusing, feel free to email me. Also, you can rewind the video. That is the power of YouTube. All right, let's take a look at what we talked about on Tuesday. So we looked at the auto ionization of water. Remember, this is like I self-ionize myself. So two water molecules will interact. You'll make an OH minus and an H3O plus. We call a molecule that can act as an acid or a base amphoteric. And this has an equilibrium constant, just like every other reaction has an equilibrium constant. But this is called Kw, the water equilibrium constant. And it's simply the concentration of OH minus times H3O plus. At 25, Kw is 1.00 times 10 to the minus 14. And that's where we get a pH of 7 from, being neutral. Because if you are a neutral solution, the amount of OH minus is equal to the amount of H3O plus. And if it's 25, both of those have a concentration of 1.0 times 10 to the minus 7. Hence, pH of 7. When you do the pH of this number, you get 7. And then we looked at 76A. If given an OH minus or H3O plus concentration, can we solve the other concentration? We can using Kw. And then we have to decide if something's acidic or basic, right? If you have more H3O plus than OH minus, you're acidic. More OH minus than H3O plus, you're basic. Same amount, neutral. We did 76, the other ones in class. Then we looked at pH. pH is minus log H3O plus concentration. You can also do POH minus log OH concentration. pH plus POH is equal to 14. And pH is a logarithmic scale, which means from going 2 to 1, you are 10 times more acidic. 3 to 2, you are 10 times more acidic. 3 to 1, you're 100 times. pH, any number below 7 is acidic. Above 7 is basic. 7 is neutral. Then we did problems on 78, figuring out how to do pH and POH. Remember what you're looking at here. Then we talked about how to calculate the pH of a strong acid. Remember, a strong acid breaks down 100%. So whatever your starting concentration is your concentration of H3O plus. So you just do minus log of that. We did a problem with that. And then where we ended on was the pH of a weak acid. For a weak acid, you need to use an ice table. And we just briefly mentioned problem 80A at the end of Tuesday, and that is where we are going to pick up. So let me open up a new Canva here. Dun, dun, dun. All right. Let's do problem 80A. So what is the pH of a 0.250 molar hydrofluoric acid solution if the Ka for this solution is 6.8 times 10 to the minus 4? Right, that's supposed to say 0.250 up there. All right, so for any acid reaction, the first thing you always want to do is the same. You write down your acid, how it's going to react with water. All right, so acid gives a proton to water to make H3O plus F minus. You want to write your Ka expression. This is A because it's an acid. That's product over reactant. So H3O plus, and I forgot they did the states. You can always assume your water is going to be liquid. Everything else is aqueous. H3O plus multiplied by F minus divided by HF. Remember, I want pH, that's what I'm doing, so I want minus log of H plus, right? That's what pH means. So I need to figure out what H3O plus is. So we can set up our ice table to do that. So when you are dealing with a weak acid, use your ice table. Liquids, we don't need. All right, so our initial is 0.250. H3O plus is 0, F is 0. We can calculate our Q based on initial concentrations. Remember, Q is the same thing as KQ, just not at equilibrium. So Q is the concentration of H3O initial 0 times F minus 0 divided by HF, 0.250. This Q is 0, and if Q equals to 0, that means you make products. That means we're going to lose reactant. So we do minus X, X, X. So we have 2.50 minus X, X, and X. Now, for the strong acid problem, we knew what X was because it's strong acid, breaks down completely. It's what you started with. However, weak acid, we don't know that. We don't know how much it's going to break down. So what you need to do is what we did for the other ice tables. You need to plug the E column into your Ka expression. However, before we do that, there's a minus X here. Whenever you have minus or plus X, check the X is small approximation. So our concentration is 0.250 and our Ka is 6.8 times 10 to the minus 4. So remember, for this approximation, take your K, 6.8 times 10 to the minus 4, multiply by 100, which is 6.8 times 10 to the minus 2, or 0.068. You're asking, is my initial concentration still bigger than this number? 0.250 is bigger than 0.068. So remember, what that means is that at equilibrium, I can ignore the minus or the plus X. All right, so this is valid. So let's plug our E into our Ka. So Ka was 6.8 times 10 to the minus 4. H3O plus, F minus at equilibrium. They are some variable X. We need to figure that out. HF at equilibrium is 0.250. So I'm going to multiply each side by 0.250. And I'm just going to bring it down here. So let's do our calculator. All right. So we have 6.8 times 10 to the minus 4 times 0.250, 0.00017. So 0.00017 equals x squared. We want to do the square root of each side. So equals the square root of A1. X equals 0.0130. All right, and that is my H3O plus concentration. So I want to figure out pH, right? So at equilibrium, this is 0.0130. pH equals minus log of H plus at equilibrium, which is 0.0130. And let me do that. So pH is 1.88. So that is the answer to this problem, to ADA. pH is 1.88. Now, one thing I do want to point out is let's check that X is small approximation. When we use that, we said X was 0.01. So imagine that I didn't use that approximation and I did the quadratic. I would get a number that's close to 0.01, which compared to our initial is a 0.5% of our initial concentration, which means my pH is off by 0.5%. So if I did the quadratic, I might get a pH of 1.89. Not enough difference for me to care. That is why we use the X is small approximation. Saves us some time. All right. So for this, there's also ADB. I'm gonna let you try to do that on your own. If you have questions about it, or if you want to see if you're right, let me know. Check to your classmates. But I do want to do 81 together. All right, 81 says you have a 0.185 molar weak acid solution. The pH is 2.98. So what I want you to do, and this is a time to pause the video, is I want you to write your equation with HA in water. What are you going to make? Again, this is good practice. Then 2, after you do that, well, 2, I guess, 2, write your Ka expression. 3, your ice table. So pause, do that, come back when you have it all set up. All right, and I am going to go through it now. Remember, acid gives a hydrogen to water. So we have H3O plus A minus. State symbols AQ. Liquid AQ. AQ. Let's set up our ice table. ICE. Liquid we don't care about. Oh, I forgot step 2, your Ka, right? Ka equals H3O plus multiplied by A minus over HA. So our initial concentration is 0.185, 0, 0. Let's check Q. Q is H3O, so 0 times A minus 0 divided by 0.185. So here Q is 0. So we're going to make products. That means we lose reactants. Don't assume Q is always going to be 0. In our practice problems, that does happen. But always check it, right? So minus X plus X plus X. 0.185 minus X, X, X. All right, so this is the same situation we found ourselves in problem 80. And remember, from here, we plugged the E into our Ka after we checked the X is small approximation. But there is a problem. We don't have a Ka. So if I plugged my E row into my Ka expression, I would have 2 variables. I would have X and I would have Ka. And that's actually what the problem is asking. It says, what is Ka? Please calculate Ka for me. All right. So we can't plug it into Ka, but we do have the pH, right? pH equals minus log of H plus concentration, which here is 2.98. And the way to convert between a hydronium concentration and a pH is that you do 10 to the power of negative pH. If you have a pH, do 10 to the power of negative that number, you'll get your hydrogen concentration. So I'm going to do 10 to the power of negative 2.98. Which is hydronium is 1.05 times 10 to the minus 3 molar. So that is the hydronium concentration, and that's how you solve 81. Again, if you have questions about what we did there, email me, come and see me. But with that, we are going to continue on. I know I'm going quite a bit faster compared to class, but again, you have the power to slow down and rewind. So let's go to section 17.6, which is percent ionization. What percent ionization is simply what percent does your acid ionize? And for strong acids, that's easy. It's 100%. That is what the definition of a strong acid is. It dissociates 100%. The percent ionization is 100. However, for a weak acid, we need to calculate H3O plus at equilibrium. And then our equation is H3O plus at equilibrium divided by HA initial times 100%. Or if we want to think about it in the ice table, for your acid, this is, whoops, your initial is down here and your change is here. Because remember, for an acid, if you don't start with any H3O plus to begin with, which is what we're thinking about, it's going to be how much acid broke down. So let's do a problem that looks at percent ionization. That is 17.6. And that problem says you have a Ka that is 4.6 times 10 to the minus 4. I want to know percent ionization of a 2.5 molar HNO2 solution. Oh, excuse me, 1 second. All right. So let's take a look at this problem. So the first thing we want to do is write down the equation of HNO2 with water. So HNO2 plus H2O makes aqueous liquid. So HNO2 is our acid. So we'll give it to H2O to make NO2 minus plus H3O plus. From there, we can set up our ice table. Well, we can write our Ka. So that should be our second step. We can write our Ka. Aqueous, aqueous. So NO2 minus H3O plus makes HNO2. Remember, water is a liquid, so we don't have that. Now, let's set up our ice table. Liquid, don't care. HNO2, we have 2.5. No NO2, no H3O plus. We can check out Q. Q is the same as K, just initial in this case, so 0 times 0 divided by 2.5. Again, Q is 0, make products. So we lose reactants, make products, make products. I plus C equals E. 2.5 minus X, X, X. All right. So remember, we're trying to find H3O plus at equilibrium for percent ionization. Here we have a minus X plus X. So let's do the X is small approximation. So Ka is 4.6 times 10 to the minus 4. Multiply that by 100. The 4.6 times 10 to the minus 2. Yeah, 2.5 is bigger than that. So I can ignore the minus x. And now we can plug this into our Ka expression. So Ka was 4.6 times 10 to the minus 4. Right? That is equal to NO2 concentration x multiplied by H3O plus concentration x divided by 2.5. I'm going to multiply each side by 2.5. So I get 4.6 times 10 to the minus 4 times 2.5. And whoopsie doodle, 0.00115 equals x squared. I'm going to square root everything. So the square root of A5. So x equals 0.0339. So that's what x is. So at equilibrium, the amount of H3O we made was 0.0339. Again, small compared to 2.5. That's why our approximation is valid. Let me erase that line. Did not mean to make it. All right, so now we want percent ionization. That is our H3O plus at equilibrium, 0.0339 divided by our initial acid concentration, 2.5 times 100%. No, 0.0339 divide 2.5. Take that number times 100, and our percent ionization is 1.36%. What this means is that of all of our starting acid molecules, only 1.36% lost their proton, right? So that's what it means to be a weak acid. Now, if you pull up the notes, you'll see there are extra practices for percent ionization. There's one that's called just extra practice, and then question 82. Try these out, right? See if you can get them. If you struggle, have a question, let me know. Otherwise, I'm going to pull up a new PowerPoint on my tablet that I have with me. And for those of you who like to follow along with the PowerPoint as well, this is the Tuesday, March 26th PowerPoint now. That has percent ionization in it. So we just did that. So let's go to section 17.7, which is basically bases. And bases work the same way as acids. And I already mentioned this, but bases, their equilibrium is called a Kb, not a Ka. They make OH minus, not H3O plus. And so generally we will do a POH, not a pH. So from your book and on the slide, I have example 17.11, which is what is the OH minus concentration and pH of a strong base? And what I would like you to do is try B, right? B has 0.0015 molar SrOH2. So what I want you to do is write, this is a strong base, so write your equation plus water, right? And then tell me how much OH concentration you have and then what your pH is. Feel free to pause the video and do that. See how far you get or you get stuck. But I'm actually going to go and solve it right now. So at least try it before you watch the solution. We have SrOH2. We're going to add water to that. Let's see what we make. So water molecule is our acid. It's going to give a hydrogen to our base. However, we have two OHs, and we talked about this already, but let me draw it. So you have SR2 plus. I know it's 2 plus because OH minus is 1. Surrounding this are two OH molecules. These are my bases. And so one water molecule will give one hydrogen to this base. The other water molecule will give the hydrogen to this base. And what you make is SR2 plus 2H2O plus 2OH minus. So I actually need two waters to balance this out. Right? And remember, I want to figure out what this OH concentration is. So it's a strong base, but we could use an ice table if we wanted to. So let's do that because I'll show it to you what this is going on. So liquid, aqueous, aqueous. Let me write my state symbols. Liquid, aqueous, ICE. All right, anytime there's a plus or an arrow, I get to draw a line. Waters, liquids go away. All right, my initial concentration is 0.001500. All right, this is strong, so I always lose reactants. Minus X, plus 2X. All right, and so strong base concentration is 0 at equilibrium, which means X must be 0.0015 because it's 0.0015 minus X equals 0. Just lost my line. So 0.0015, and this would be 2 times 0.0015. So at equilibrium, we have 0.0015, 0.0030 OH minus. So the concentration of OH minus at equilibrium is 0.0030. We can calculate a pOH from this, minus log of your OH concentration. So minus log 0.0030. So our pOH is 2.52. And then we have pH plus pOH equals 14. So pH equals 14 minus 2.52, right? Which is minus pOH. So that's like 11.48. That is our pH. So the thing to take away here is that your bases can have your strong bases can have multiple OHs. And let's just briefly talk about, what are strong bases? So what are strong bases? And generally for us, a strong base will be a metal plus OH, right? So lithium hydroxide, potassium hydroxide. We just talked about strontium hydroxide, calcium hydroxide. Generally, if you're seeing a metal plus an OH, just assume that's a strong base. It will break down completely. And there is some extra practice there for you as well. So feel free to check that out. But we are actually going to move on to section 17.8 now. Remember, if you don't quite get this, look on the PowerPoint for those extra problems. Try those. Come see me, come see tutor, come go see Alyssa, ask your classmates. We can help you with those. But let's go to section 17.8. And section 17.8 is ions, and ions can be bases. And basically, as the title says, some anions, remember this is a negatively charged molecule, can be a base. So A minus is just my generic anion. So let's take a look at how this would happen. So if I have an anion in water, right, that anion can be a base. Take a hydrogen from water to make HA plus OH minus. So an example of this, right, a real life example would be like F minus or HS minus. So really, we have to know which bases would be, or sorry, which anions would be strong bases. And there's one thing we have to realize. A strong acid, something we say is a strong acid, does not make a base. A weak acid does make a weak base. So a strong acid can't make a base. A weak acid can make a weak base, and vice versa. A strong base, I can use the other words here, right? A strong base does not make an acid. A weak base does make a weak acid. So let's start with a strong acid to see how this is going. So our strong acid is HCl. And HCl, we're going to interact with H2O like we've seen to make H3O plus and Cl minus. All right, so we have an anion, Cl minus. So the question is, will this anion make, or will this anion be a base? That's the question we're asking. So let's do this experiment. So let's say that Cl minus was a base. This is just an experiment. So let's say Cl minus interacts with H2O. And so if this is a base, I'm going to take the hydrogen from you and make HCl plus OH minus. However, look what we created. HCl. As soon as you create HCl, remember what HCl is? It's a strong acid. So this will happen immediately, that HCl will react with a different water molecule to recreate Cl minus plus H3O plus. So in essence, no chemistry happened with Cl. Cl minus is not a base. It can't. Remember, a base takes a hydrogen from water. Cl minus would create HCl, which is a strong acid. So your rule of thumb is, if I have an anion and I do a reaction, a base reaction with it, and if I create a strong acid, that reaction can't happen. Right. So if I have an anion and I reacted with water to act like it's a base, and I create a strong acid, which in this case HCl, that reaction that I just wrote down can't actually work. So let's actually talk about, what are our strong acids? How do I determine if I have a strong acid? So strong acids, on a problem, right? How do I determine if I have strong acids? One, no Ka is given. If no Ka is given and I don't ask you to find Ka, we can assume it's a strong acid. Two, know these strong acids: HCl, HBr, HI, H2SO4, HNO3. Right? If you see these 5 molecules, You can just assume it's a strong acid. Now, let's look at a weak acid though. So I said a weak acid makes a weak base. So let's take a weak acid of hydrogen cyanide. So hydrogen cyanide, I'm going to tell you, is a weak acid. And so when hydrogen cyanide reacts with water, I'm going to take a hydrogen. Whoops, I'm an acid. I am going the wrong way. I'm already jumping ahead the bases. So HCN, it's a weak acid. So I'm going to give the hydrogen to water. And I'm going to make Cn minus plus H3O plus. So I have an anion. I have a negatively charged anion. So let's see if this can act like a base. So I'm going to react that with water. So I'm a base, so I take a hydrogen from my acid, and I make HCN plus OH minus. HCN is not on our list of strong acids, so this is a possible reaction. So Cn minus is a base. It is a base. So I know this is confusing for people when you first look at that. So let's do 17.13, example 17.13. This is from your book. And I have 3 anions, NO3 minus, B, NO2 minus, C, C2H3O2. Whoops, 2 minus. What I want you to do is react them with water, right? Draw out your reaction with water and ask yourself, when I do that, did I make a strong acid? Based on the list we just talked about, did I make a strong acid? If yes, not a base. So pause the video and try that. All right, so let me do this. So A makes HNO3 plus OH minus. We go back to our previous slide. HNO3 is a strong acid. I create a strong acid. So NO3 minus, not a base. It is pH neutral in water. It doesn't react. Because if I reacted, I would immediately create a strong acid, which would recreate my NO3 minus. B. So I make HNO2 plus OH minus. Sorry, I had another coughing fit there. HNO2 is not on our list of strong acids. So yes, NO2 minus is a base. Let's do our last compound, C2H3O2. Yeah, it was supposed to be a 2. So you make HC2H3O. And you ask yourself, is this a strong acid? Yeah, it's not. Oh, excuse me. So this is a weak acid. That means what we did create is a base. Okay. So I think due to my throat being in pain right now and coughing every couple of minutes, I'm going to end it there. And on Tuesday, we are going to look at metals and kind of review this as well, how metals can act like an acid. But again, there's plenty of practice problems in this PowerPoint, so I want you to try those. And if you have any questions about anything we did today, see me in my office or um, email me. Otherwise, hope you all have a lovely weekend. See you next week.